So we've already talked about this. We had a lab a few weeks ago. When we had that lab, we went outside and there was ants and there was sand and there was buckets and there was sun and it wasn't, oh. All right, it was amazing. Now, the sun, it was hitting these things, but their temperature was different because we had some at angles, some at not angles. And you all agree that the sun does heat things differently, yes? Yes, I thought so. And that's actually what causes some of our weather. The sun unevenly heating things. Now, next question. We just said that the sun heats things different. And that does cause different temperatures, yes? Yes, we definitely agree with that. So there's another statement. The uneven heating of Earth's surface by the sun will cause different temperatures. All right? So we're good with that statement. Next thing I want you to do, I want you to fill in the blanks that I'm about to put up here. Now, I'm sure you've already heard this phrase before, so let's just see. Have you ever heard warm air rises and cold air sinks? That's right. Warm air does rise, cold air does sink. Now, warm air rises. That rising warm air, that when it rises, it spreads out. When things spread out, they have less pressure. So warm air rises, it spreads out, it has less pressure. So warm air has low pressure. Cold air, it sinks, it gets all close together, and it increases the pressure in the area. So cold air has high pressure. That would be a good thing to know. Warm air, low pressure. Cold air, high pressure. Air always moves from high pressure to low pressure. Always moves from high pressure to low pressure. Now, on your fill-in sheet right now, I want you to add something. You just wrote that air moves from areas of higher pressure towards areas of lower pressure. Right under that word higher, I want you to write the temperature. High pressure is cold. So right under there, I want you to write cold. So high pressure is cold air. And low pressure is hot air. Okay? Write that under there, highlight it, make sure you know that we could say it goes from high pressure to low pressure. We could also say it goes from cold to hot. So air always moves from cold to hot. And I'm going to revisit this. It's going to be kind of a theme that we're going through today. It's going to move from cold to hot as we're going through. And it's going to create these little circular cells. So right up here, we do have a lot of little circles that are just circulating, if you will, around the globe. Whoa. And this causes our wind. Wind is the movement of air caused by differences in air pressure. Remember, the high air pressure is the cold, the low air pressure is the hot. And these differences cause our wind. Cold air is always at the poles. Would you agree with that? Yes, North Pole, South Pole definitely has our cold air. And it creates high pressure. Then the warm air around the tropics. That is our low pressure areas, and those two things are going to circulate. They're going to try to find some middle ground, and that creates a global wind. So these are worldwide winds every 30 degrees of latitude. So every 30 degrees of latitude across the globe, we have global winds. We're going to learn what they're called in just a minute. So that is the Coriolis effect. If you're in the northern hemisphere, things are going to curve one direction. Because the earth is spinning, these lines of wind cannot go straight from north to south because the earth spins. It's going to make those winds curve. If you're in the southern hemisphere, they curve in the opposite direction. We just saw the balloon demo. We saw how those winds are going to move around that balloon, just like they move around the earth in a curved pattern. The Coriolis effect. Whoa, buddy. Keep going, yay notes? Yay notes. So right here, you can see the black lines. These are the ones that are trying to do these straight line winds from north to south, or south to north. But we know that that's not actually what happens. The purple is what actually happens. They're going to curve. They're going to go around. And that's the what effect? There we go, the Coriolis effect. Now, some points on the earth are going to travel faster than others. Whoa. Think about this. Those of you track stars in here. Those of you football stars who happen to get in trouble from time to time. What does the coach tell you to do when you get in trouble on the football team? Go run. They say go run a lap. Go run 2 laps. Now, when you go run that lap, are you going to go run in lane 1 or are you going to go run in lane 8?
Lane 8.
Lane 1.
Okay? Quiet. We all know the best choice would be lane 1 because it's a shorter distance, isn't it?
Yes.
Everything closer to the center, just like on this globe, everything closer to the axis is a shorter distance. Now, every day, every 24 hours, the Earth spins around on its axis, right here. But these spots right there on the poles, they don't have to move very far, do they? But right here, that'd be like lane 8 on the track. That's a lot further. It's going to have to go all the way around in one day, where down here at the poles, it's just a little bitty bit. So that's a long way it's going to have to go around. So the edges of the Earth, right there at the equator, that's going to have to move a lot faster every day to make it that same distance. Does that make sense? Okay, so it's moving a lot faster on the edges, and that's going to cause those curves. It's going to make the wind change about every 30 degrees of latitude because that's different distances away from the axis. So when you get a little bit further out, it's going to make those winds change. You get a little bit further out again, it's going to make those winds change. So about every 30 degrees of latitude, the winds are going to change. Now the next thing we have. Oh, we can go back. So right here. How would these purple lines change if the Earth is spinning even faster? Right here, every 30 degrees, we have a change of winds. So if we're going even faster, what would happen?
Less.
Yes, we would have more changes of winds. So right here, we have a change every 30 degrees. If we were going even faster, we'd have a change every maybe 15 degrees instead of every 30 of latitude. So each one of these changes would happen more often. So these global winds, these are the global surface winds. They have specific names. What we're going to call them are the polar easterlies. Those are at the poles. Polar, poles, makes sense. Then we have the westerlies, right next to the easterlies. And then we have the trade winds, all hovering the equator. So we have the polar easterlies, we have the westerlies, and we have the trade winds. Now on your page, you have a globe. I would go ahead and label these winds on your globe now. Another thing I want you to go ahead and label on your picture of the globe right there, the equator line, that is right between the two trade winds, we're going to call that the doldrum. And I'll explain in another slide or two what that is, but go ahead and just label it on your picture for now. That line at the equator right between the trade winds, we're going to call that a doldrum. And the 30 degree line right between the westerlies and the trade winds, we're going to call that the horse latitudes. The horse latitudes. And that's going to be on the top and the bottom. So right between the westerlies and the trades on both sides, that's going to be called the horse latitudes. All right, so what I told you is the trade winds, when they meet up, these winds right at the equator line where the two types of trade winds, the northern and the southern trade winds meet, they're going to hit an area where the wind actually stops. You're going to get very little wind. You had a lot of wind and now you're going to get very little. This is called the doldrum. So it's that border between the two. And the horse latitude, same thing that happens, but it's a different border. It's the border between the westerlies and the trades. And these right here also, the air is going to stop moving. This is a big deal if you're in that in the olden days when you have the ships that depend on the wind to move you around. Oh my goodness gracious. All of a sudden, you stop moving, no wind, bad things happen. Another thing, very interesting. In that other class that you've been taking across the hall, I know you've been talking about some trading that's going on in your history class. So you all been talking about trading? The triangle trade, things like that. They're trading goods, they're trading people, they're trading all kinds of things in that history class, right? Why is it called the trade winds? Ever wonder about that? The trade winds? Oh, let's look. So we have this picture, and the trade winds. So we're going to start right over here. This is like the tip of Africa right over there. Let's take these words off real quick. So we have the tip of Africa right here, and we have some of that trading going on. And which section is this in? The trade winds. Because these are the winds that are powering the ships that are making these trades over here, up here, and back. That makes the triangle that you learned about in that history class. You mean like that history stuff and the science stuff actually has something to do with each other? No way! Sort of like, y'all just learned about that Boston Tea Party, right? And in the Boston Tea Party, they were actually at a low spring tide. Did y'all talk about that in the history class? Okay. Quiet. It was actually a low spring tide when that was happening. So, all those Bostonites, they went and they boarded the ships, but the ships, since it was a low spring tide, that's the lowest of the low, they're actually sitting in mud. They weren't in the water at the time. They're in mud. And they boarded it, and they started very sloppily throwing the tea over. Then they went and jumped in the mud and like spread the tea out. So it's not like those pictures that you see, because that just looked kind of weird if, they drew pictures of these ships in the mud and the tea going over. But when you read the actual accounts, that's what was happening. It was a low tide that day, low spring tide. So the ships weren't even able to sail away. They were actually in the mud. About 6 hours later, they would have been at the highest tide. But at the time that they boarded them, they were low, so the ships couldn't get away. And then, boom, all the tea goes over. Good, fun stuff.
Yay!
Yay, history and science. So another thing that I want to tell you a little bit about, the trade winds. How powerful these things are and how global they are. The biggest desert in the world is the Sahara Desert. It's shown right here in Africa. And that thing, the winds, the trade winds, can actually blow the sand from the Sahara Desert, and it can actually reach Florida. Whoa. So the wind is actually a global wind. It will travel worldwide. It can blow things all the way from Africa to the tip of the U.S. Whoa, buddy. You should know this. If you've been outside in the afternoons, all the construction going on around here, we're getting sandblasted every day when we leave school. Would you agree with that? You walk outside, you open your mouth, and it tastes like dirt. The winds in our area are blowing the sand, just like the trade winds can blow the sand from the tips of Africa all the way over to the U.S. Whoa, buddy. Now, another global wind that we cannot feel. Everything we've talked about up to now has been a global wind that we could feel, a surface wind. Now we're going to talk about some that we cannot feel. The jet stream is actually 7 kilometers above the surface. And it's always blowing. It's a big deal for that airline when they're flying that high up there. They can either get in the jet stream and they're blowing and it's going and it's helping them get to where they're going faster. Or if they're going the other way, it's slowing them down the whole time. Whoa. And jet streams, just like many of the others, they are based on temperature differences. we have two main jet streams. We have a polar jet stream. And can anyone guess where that is? Near the poles, yes. We also have a subtropical jet stream, and this one is closer to the equator. It's in the tropics. So if you looked right here, I bet you could guess that the blue jet stream is the polar, and the red jet streams are the subtropical jet streams. Continuing. Next thing I need you to do. On your paper, there are 4 things that you're going to draw. You're going to draw a land breeze, a sea breeze, a mountain breeze, and a valley breeze. You need to be able to describe what's happening at each of these local areas, where the wind is going, where it's coming from, where the temperature changes are happening, and whether it's day or night based on the wind and how it's moving. So these are not global winds. These don't go from one continent to another. These are winds that are just in a localized area. This one right here is called a sea breeze. Sea breezes always happen during the daytime because you can see the sun right there. The sun is going to come in, it's going to heat up the land. And we know that the land heats up faster than the water. So this land is going to get really hot during the day. And we know that hot air rises. Hot air does rise, yes. I have heard that before. Hot air rises. And it's going to go straight up. Look at that. And then it's going to keep moving. It's going to come and go over here. When it gets over the water's not as hot. So that hot air is going to start to cool down. When that hot air starts to cool down, it's going to sink. So now we have the hot air. It's cooling down. It's sinking. Because cold air sinks. And then it's going to continue to go around. And we know that air always goes from high pressure to low pressure. So it's going to go from cold to hot. So that air is going to seek out that hot spot and it's going to flow in there. It's going to create a convection cell. A convection current that is constantly looping. So during the day, if you're in an ocean town, the air is going to be blowing from the sea towards the land. Because it's going to be blowing from that cool spot to the warmer land. Whoa. So you're going to feel that breeze in your face. Now, a land breeze is a little bit different. A land breeze happens at night. So you notice the moon in this picture. We see the moon in this picture. Now all of a sudden the sun is not heating the land more. The land is cooler. The water is the same temperature, but the land is cooler. So the warmer water heats up the air. The air goes up. It starts to cool off and it comes back down over the land. And it's still the cooler air goes towards the warmer. So that air is rushing out to sea now. So the wind shifted. So at night, now the wind is blowing from land to water. So it's the exact opposite. You're going to have to be able to tell the difference between these two. You're going to have to know where the water where the air comes from and where it goes to, where it's hot, where it's cold. The last 2 things you're going to have to be able to draw and identify is a mountain breeze.
Oh, no.
Wait. The last thing that you're going to have to be able to identify is a mountain breeze and a valley breeze. These 2 things work the same way, but they don't have to do with the water. It's just the air in the center or the air close to the land, creating a difference in temperature. Right here, at night, you're going to get a mountain breeze. During the day, you're going to get a valley breeze. They are based on the same principle, where it is warmer and where it is cooler. And that sums up the notes on the day. Thank you.